Welcome to Hot Chips 33. Keynote 1. Does artificial intelligence require artificial architects?
Welcome to Hot Chips, whatever your time zone might be. I'm Fred Weber from the Hot Chips Program Committee, and it's my great pleasure to introduce Aart de Geus, the co-founder and co-CEO of Synopsys, to give the keynote address for Hot Chips this year. If you design chips, you certainly know Synopsys. And if you've followed EDA at all in the last 30 years, you almost certainly know Aart. Aart and Synopsys revolutionized design by making RTL synthesis a reality, and they've been at the center of almost every advance in EDA since then. This has given our industry a Moore's Law-like improvement in design capability to match the Moore's Law of semiconductor design and make possible the advances we've done over the past 30 years. Please welcome Aart for his keynote talk titled Builders of the Imaginary, from Artificial Intelligence to Artificial Architects in the Era of Sys-Moore.
You know, I will never forget that day. I was a young undergraduate engineering student in Switzerland, and in the local town there was an exhibition of artists that were intellectually disabled. What I saw there was super enabling. They had an ability to see the world from different perspectives, a diversity of insight, and the color utilization was just fantastic. I also liked the title of the exhibition. I still have the poster in my home office, and the title was Builders of the Imaginary. And here we are, many years later, and I find I have the opportunity to take to you and find out that Hot Chips is where you find the greatest architects, the leading designers of chips. What a privilege. And suddenly it occurred to me, you are the builders of the imaginary at a time where imagination is becoming possible to a degree we have never seen before. Actually, you're sitting at the beginning, at the dawn of a new era, Sys-Moore, systemic complexity, but with a Moore's Law ambition. And you're sitting in the middle of that because you determine the options of the architectures, and you determine how they will support the opportunities above, and let us implement the optionality below. So it's clear to me what your mission is for the next 20 years. Your mission will be to architect intelligence. Now, you know, intelligence is sort of a highfalutin word, sort of Mensa membership type stuff. So let's humble it down just a little bit. Let's call it architecting smarts. And there's a lot of architecting of smarts that has occurred that has big impact on life. Going back a little bit, you find fire. Great way to get more calories out of food. Of course, you need to have food, and for that, you know, a plow is pretty good, except you have to schlep it around, and so domesticated horse and wheel helps a lot. And then moving forward, we see an increase of technology, step by step. Notice also how timing compacts itself, and all of these are exponential until we, of course, arrive at the modern age where the digital revolution, as we used to call it, has impacted everything. And now suddenly, in a very short time frame, this ambition of smart everything, of AI to come about. So let's have a look at how these came about, because they all have the same characteristic. It starts invariably with some great accidental or brilliant idea. Most ideas, by the way, don't work, so you need to wrap some engineering around it, and wrapping is the right word. Duct tape, WD-40, they do wonders. And with those wonders, you have the opportunity to suddenly close the techonomic loop. And if you do that, you get to play again. And play again typically means now adding other ideas, fusing them together, and suddenly you have the potential to see exponential impact of the innovation you bring about. Now, of course, we're quite familiar with these, but one of those that is absolutely central is fusion. And a great example in history is the printing press. Remember what it is. It is a small alphabet, 26 letters, in reusable form, mobile parts, and then the combination of fast-drying ink and stable paper, all under a screw press. And granted, it was invented already by the Chinese a long time ago. Gutenberg had the advantage of a much smaller alphabet, and the impact of this was enormous. 50 years later, 20 million books had been printed, and the Renaissance was moving forward very rapidly. Fast forward 500 years, and what do you find? Well, you know, we've improved the alphabet, only 2 letters now, and maybe with quantum computing it becomes sort of one fuzzy one. We have packaged this up in reusable parts that you are well familiar with, and then the wonders of lithography and planar transistor technology, all supported by design, EDA, and IP, have made the modern age, and most importantly, Moore's Law possible. This is the most rapid increasing exponential in history. Now, if we put this in the big picture, what we really see is that we are surrounded by 2 massive forces, still better silicon and software that impacts everything. And everything we do in this domain is always subject to the same optimization desires: quality of results, time to results, and cost of results. Or, you know, if you're on the marketing side of things, better, sooner, cheaper. You're quite familiar with those because, of course, you remember PPA. Performance, power, and area. And of course, area stood very much for yield, but today you would multiply the 2. And by the way, we have long discovered that power has an evil twin in the form of thermal effects. Meanwhile, though, systemic issues are becoming very important. Security built in, functional safety, if you're in a car, for example, or silicon lifecycle management for all the products that could age with utilization. And from the top, the interaction between hardware and software is primary. And of course, architecture determines how you're going to balance all these requirements over time in a fashion that is effective. So if we look at this, in this force field, it is useful to apply the very vision that we had. Optionality sits in the middle, and the opportunity space is now driving many things. And of course, optimality has been our profession for a long time. It sits against a backdrop of techonomics. And of course, if you look at techonomics, we have been very familiar with the ultimate push for 50 years of better and better silicon, classic Moore, growing more transistors, faster transistors, lower power transistors. Now, something has changed fairly recently, actually. Computation out of this has just become powerful enough so that new machine learning algorithms actually can be computed in time. At the very moment that we see an enormous growth in the amount of data that's available, you put those 2 together and every vertical market thinks, hey, can we do that AI thing, and can we make everything a bit smart? With other words, the tech push has turned into tech push and an onomics pull. Now, why is it right now? Well, let's look at the data briefly. And if you look at that, you see that the data generated is hard to see. The human part is actually very small. It used to be big, you know, videos and photographs. It's nothing compared now to what's generated by machine. And you see that in 2018, it actually heeled over in favor of machines generating data. At the same time, on this graph, you can see the amount of computation that has gone into learning systems, and of course, a big discontinuity just in the last 5 to 7 years. You put those 2 things together, and suddenly you have the opportunity of a market that grows very rapidly. And actually, if you look at semiconductors are doing very well right now and are very close to crossing the 500 billion or $500 billion mark. But what is interesting, Credit Suisse already forecast that the smart everything market will be above 40 trillion. Well, I don't have to tell you that that brings the mother of all pulls to move this forward. And indeed, every vertical market right now is investing to use AI to become a little smarter, more efficient, more effective. But with it comes a whole set of system requests and requirements that all have to be integrated. Well, this is what characterizes the SysMore era. Because when you look at SysMore, really fundamentally it stands for systemic complexity, in contrast to scale complexity, which we really have mastered quite well, but supported by the exponential ambition that we know from traditional Moore's law. So let's have a look at how we can progress with this, and there's a lot to do. Of course, one of the considerations is we need to increase productivity. And as a matter of fact, we would predict that in this decade, we need to increase it by about 1,000x to live up to the ambitions that together we have. Well, how hard can this be? Why don't we just continue that Moore's law thing? And actually, it has been quite effective because you have seen in the markets in the past exponential growth there as well, all enabled by great chips. Now, to do great chips, which you have done, it takes multiple ingredients. You need advancements in technology nodes, scaling of manufacturing, and the ability, of course, to test if the thing works. But you also need the ability to design using EDA, IP reuse, and by the way, you have to build in the test. What's wrong with this equation is, this is not an addition. This is actually a multiplication. A single piece doesn't work, the whole food chain doesn't deliver. Now, if I may concentrate for a moment on Synopsys, because after all, our ambition is to catalyze your exponentials. Well, we've worked hard on this for a number of years. Actually, we have a mantra for that, yes if. And yes if is the counter to no because. The if and the because may be the same, but the yes if approach opens doors. And in December, we'll be 35 years old. And at that point in time, we can actually claim to have essentially improved productivity by 10 million x. Now, I said, we now need a big yes if because we will deliver this decade another 1,000x into that. Big ambition. Now, I said, why not just do that Moore's law thing again, except if you look a little more carefully, it really looks like this. I'm the first one to say Moore's law is by no means that we are continuing to smaller devices. And it's actually fun to see that just a few weeks ago, one of the providers said, you know, we're no longer going to call it 2 nanometer. We're going to call it 20 angstrom. I do note that in the word angstrom is the word angst. And we will have to deal with a lot of technical challenges to overcome that. But what is exciting is that this age of system on a chip is absolutely continuing alive and well. But what is just as exciting is that there's a booster pack to this. I call it a booster pack to Moore's law, which is the ability to abut very closely stacked chips, actually use silicon interposers to connect them. With other words, we have just opened up now the system of chips age. And it's interesting that it happens at the very moment where AI is driving a rethink of architectures. Because if you want 1,000x in AI, you're going to optimize for the type of algorithms that you have. And so this characterizes the SysMore era. Now, personally, I'm just very partial to this notion of function and form. Maybe because I discovered that a great architect in the 1980s said, you know, form follows function. And I've known that for a long time because if you have a house where the garage is here and the kitchen is there, your function for the rest of your life will be schlepp the groceries through the whole house. Garage and kitchen need to be close together. Form must fit the function. But what I didn't know when I looked at this was that he had a draftsman that turned out to become an even more famous architect, Frank Lloyd Wright, who said, form and function should be one. And each one of you that is an architect knows this. Because if you look at this picture, you can say, yeah, there's function, there's form, and there's really physics by the time you're done. And all architects, when they develop something, they go back and forth between form and function for a while. And then ultimately it gets designed, and here you get this beautiful layout of a multi-tile device that is de facto the physics of arrival. So if you look at this picture, you can simplify it and say fundamentally there are 3 layers: architecture, design, and manufacture. But let's not forget software. It goes all the way to the top. This is what we are designing for and what we're designing towards. Now, levels of abstraction is not anything new. And I'm always struck by architects because they capture things well. You know, here, Mies van der Rohe says, well, you know, it really starts by putting 2 bricks together. Well said. But when you talk to anybody who's really great in their profession, they know everything. A great architect knows exactly the weight of a brick and exactly the weight a brick can carry. As a matter of fact, there was a cute saying by Louis Kahn who says, you know, even a brick wants to be something. Yeah. Inspiration starts at a low level and moves very high up. And of course, we know bricks extremely well. We grew up with a lot of bricks. This is what they looked like. And we learned to put them together into walls and other buildings. And in that process, intuitively, we got a sense for strength, for weight, for balance, and so on. Now, since then, maybe we have optimized our bricks a little bit. Here's an advanced transistor brick. It's a gate-all-around, or ribbon-fed, if you like. And of course, these 2 get assembled into walls or layouts. And actually, I took the liberty to take a very old layout. This comes from a great book, the Mead Conway book, that actually captured the essence of how things can come together and be automated. And of course, from there, you keep moving up and you arrive at extremely sophisticated things, such as this Intel Ponte Vecchio 47-tile super chip, if I can call it that. Well, at the high level, architects have opinions too, and Vitor Conchi says, you know, architecture is not about space, but about time. Well, in our field, we've known this for a long time, yeah? Speed and area, but speed really matters. And actually, in the Lego world, I found a good example here, which is the Babbage difference engine built in Legos, believe it or not. Of course, in many of the buildings, certainly in the Middle Ages, you know, time was more about the eternal time. And the higher up you could get with your church, the closer you were to that. Be it as it may, at each one of these levels, we have the opportunity to look up and be the architect of the next level up. And so with that, we can see that the aspiration of doing more is what we have is never ending, all the way for us now well into the software domain. Now, to give a little bit more rigor to this, a really good friend of mine of 40 years ago, actually we used to play basketball together, I remember, he almost killed me once in that, but you know, that's forgotten. He built this wonderful model, again with function, he called it, I think, behavior, form, structure, and physics. The only difference on this graph is it looks inside, meaning you're going to essentially go around the loop with tightening circles until you're in the middle of this picture. And of course, the software becomes the spec, the architecting sits more at the top, the design is there. And then I modified it a little bit. Oh, here's the tape out in the middle. I forgot to talk about that. But I modified a little bit because after the tape out, there's still a number of steps that are very important, such as optical proximity correction, layout rules checking, etc. And then the manufacturing closes the loop by, of course, bring up and hopefully not too much debug. So if you use this picture, there's a lot we can learn and automate in this. And actually it begs the question, so what has EDA done on this? Well, we've actually done quite a bit. Let me give you sort of the 20-second EDA primer. What EDA is all about is essentially, if you can capture the data, maybe you can model. If you can model, maybe you can simulate. If you can simulate, maybe you can analyze. If you can analyze, maybe you can optimize. And if you can optimize, you can automate. Oh, and by the way, don't forget the automation shortcut called IP reuse, which is unbelievably powerful. What's interesting about sort of this stack is it's not that different for AI, at least from a simplistic perspective, which is mine. And if I look at that, what I see, of course, it all starts with collecting a lot of data, giving it a model or a neural network structure, using that to train it, to then infer data out of it, maybe use that inference for some limited actions, and ultimately the objective, of course, is autonomous behaviors like a car that drives around, and safely, by the way. In all of these, it is the same characteristics of optimize for quality of results, time to results, and cost of results. So let me show you how in EDA this evolves, because we're building on that of every piece that we've done in the past. And in all fairness, you know, the first big step was early on, and that was the SPICE program. And notice, by the way, you know, this is on a log graph, and so we have kept up completely with Moore's law, or, you know, we can also say Moore's law has kept up completely with EDA. I'll let you decide. But after circuit simulation, the next breakthrough was really graphics on a computer, and with that, a lot of layout and some manual place and route optimization. And then came really a discontinuity, because the digital world suddenly started to massively blossom by the coming about of digital simulation and synthesis. That happens to be, luckily for us, also the starting point for Synopsys. And interestingly enough, before that automation, it was called computer-aided design. After that, it became called electronic design automation. And so maybe, not maybe, Synopsys was actually the first AI for design, because here is the picture that we used before creating the company. And yes, the typeset is a little fragile here because it was done on a typewriter, literally. But notice this technology X. What if technology X could take a language and actually create circuits? And the thing is, it could do that. It was actually initially a rule-based system, so some AI there. But what most people miss is that it was not just synthesis. We had actually already done the first fusion step by adding timing and, by the way, an automatic way to map into different silicon technologies, at that time LSI Logic and Toshiba. And by the way, the results compared to what humans were able to do were quite flabbergasting. So much so that a small percentage of the designers said, you know, are you going to do my job? But you know what? The majority of the designers said, this is great. Now I can do so much more. And that is really the nature of automation that we're looking for. Now, the next very big breakthrough, I think, in productivity was really IP reuse. And I want to give really full credit to ARM, because ARM in the processor, specifically the mobile processor, really set the stage to do an enormous amount of reuse. Now, Synopsys has become sort of the complete complement to that. And today, we have an enormous library of very, very, very sophisticated parts in a different set of dimensions. Notice, by the way, 3D IC, because that itself is its own category. But I like to highlight it with a little bit more color here by showing all these eye diagrams. And the reason I do that is because now that we're looking at multiple chips, we're also looking even harder at the latency, the speed, and the capacity of communication. And you know, these eye diagrams are super sophisticated, and 4 nanometers absolutely in production today. Which brings me to the next big productivity change, and this is fusion. You saw it introduced historically, but fundamentally it came about with the following thought. We have many programs that are used typically one after the other. So, for example, synthesis followed by place and route. And they work pretty well. Sometimes they go in one direction, the next one corrects it a little bit. So the thought was, what if we could look at this and say, what do they have in common? Where do they support each other, and where do they fight each other? And use that insight, which is very complex. All of these hexagons are sort of algorithms, and you add back the synthesis and place and route around it. And then, of course, make sure that you have timing optimization and characterization. You do the same with power. Do not forget that test is absolutely imperative, and make sure that you make it correct by construction by having physical verification built in. Well, this is Fusion Compiler. By now, we have 500 cases, customer cases, and plenty of evidence that it is substantially able in reducing the amount of work and getting better and better results. And so applied now to the most advanced cores and chips, you will see in a minute how important this is for the next step. But before we get there, of course, the question is, well, machine learning. Are you guys not using it? What's happening to that? We're using it all over the space. Every one of our products at this point in time has some machine learning that amends the traditional algorithms. So we use it as essentially an additional compute form that is very complementary in helping optimize certain things. But you may ask, that's cool, and that makes the products better, but what can you do on the design flow? And that is really the big question, which is it possible to use AI on a substantial number of design steps, which is in some way characterized by, can AI design chips, or is autonomous design possible? The answer is yes. And what I'm going to show you today is results that initially when I saw them, I couldn't believe we could do this. Now, how hard can it be, right? After all, a number of great problems have been cracked by AI. Chess, of course, in the late 90s. Not that long ago, the Go game. Congratulations to Google. They did just a fabulous job on this. And you can see how they sort of rate the complexity of the problem. And then recently, there have been a number of papers on what you can do in placement. And notice, by the way, complexity is going up. I would say, though, you know, the first two are in a category of win-lose. With other words, the objective function of what you want to try to do is very, very well understood. The third one is actually better worse. With other words, they are trade-off and judgment calls. Now, what we at Synopsys do is this, real chips. And with real chips, the number of variables are enormous. Actually, I want to tell you that I know exactly what each one of these question marks is. But to be honest, I'm not sure if I just should not add 2 or 3 more to it. Is this impossible? Well, to be seen. What is clear, the mother of yes if has to be applied here and see what we can do. So let me tell you what we implemented. What we implemented, we started a Fusion compiler, which has all these capabilities already synchronized with each other, fused with each other. And of course, you'll apply this to a search space that I grossly simplified into 3D and used only performance, power, and area. But the reality is it's much, much, much more multidimensional. And so what we do today, what you do today, is use the most advanced tools and your own smarts to essentially explore the space using Fusion compiler. And you get relatively quickly quite good results. But you can see by changing the constraints, by changing the hints, maybe changing some of the floor plan, you may end at different places, and hopefully there's some areas that look very promising and that you can actually do something with. Now here's what we try to do. We wrap some computation around it. We now let AI decide what to do, and we aim not at design space exploration, but design space optimization. Ergo, the platform name of DSO.ai. So we have a whole new design platform that uses literally everything we have learned in the past. Now I can hear you say, yeah, Art, that's a nice slide, but that's PowerPoint, yeah? Yes, it is PowerPoint. So ta-da, here comes the result, because this is still PowerPoint. This is how it works. You use this to find many, many different points. And hopefully, some of those will be better than what you had, or regions that you didn't explore, and you can move forward. Well, here's actually my ta-da, the real click, the results. And I have to tell you, all of these results are real designs done by real customer designers that have real careers and are betting on this. So let's have a look. So notice, by the way, the date. So this is in December 19, so it's a year and a half ago. And this is an example where the starting point was right here, and you see the power and timing axis. This is what the target was of the customer. This was the best human effort after many months. And now we're going to run the DSO algorithm. And so you can see it initially exploring a pretty broad space. You saw some better points there, so it improved the results already. And now it's working really hard. Let's see if it can do, it's still a little bit better there, still a little bit better. I'm rooting for this thing. Yeah, let's see where it lands. And there we go, the best result. When I saw this the first time, I must say I was blown away by it. I couldn't believe how good this was. And I saw something else. What I saw was this. And I had seen this before, because 30 years before, synthesis was looking at speed and area, and we always drew the banana curve, the trade-off curve. Now, in this case, it's really sort of a banana surface, but it shows sort of the best this algorithm can do. Now, notice in the title it says untrained. Now let's bring some learning into this, and here's the trained version. Starting from the same starting point, you will see the dots as they appear. Notice with how few tries, it got a better result, moved the banana curve, and this is the essence of what we will do more and more of. The ability to learn from some chips. For derivatives, of course, this is fabulous, but even new chips, much of the learning does apply from the past. But most importantly, it's this ability to judge how good something is that is essential to this AI algorithm. Here's another example. In this case, the previous one was, I think, a microcontroller. This is a CPU. And this is the best results found by the designers. Again, initially the untrained version. And what you see here is it's working hard. This is like, an algorithm on a mission, sort of a hunting dog after, a PPA type of animal to go for. And you see it pushing in the right direction. Once it's sort of found its groove, it's heading there, and substantial difference from what we could do before. If we now make it trained, notice how quickly and how impactful the results are of this. So this is what we're doing, and now by now for these results we're at about March 2020, and this is a great example because actually our customer themselves, these are their representation of what they saw. In QR they diagnosed significant power reduction, which was the most important thing to them. Secondly, a much faster convergence on results, and third, these results were obtained by a single engineer instead of a whole team of experts. So you can imagine that that has impact going forward. Just one more example, and this is an interesting one because this is one, I think, for some mobile AI device or so, where they also try to tune the voltages. And here, actually, the designers themselves created their own banana curve. Maybe they're looking at different applications or so. So let's run DSO on that, and very quickly you can see a broad exploration of the space, and frankly some quite amazing improvement. Here's the banana curve, and you can see it is both substantially faster and also lower power. And so I said these are all real examples, and it's just exciting to see the progress. We're now in June 21. Now, by the way, it just happens to be that today one of our customers said, hey, we're really committed to using AI in design. And that is just music to my ears, of course, because I think this will have huge impact on our future. Just one more example. Actually, it's sort of my favorite example. In this case, we authorized the system to change the floor plan, evolve the floor plan. So here's the starting point again. Let me just kick it off, and you can see the dots that it's getting. And what is exciting here is not only that clearly it explores some points that are in a better part of the space, as the banana curve here indicates, but what I loved about this one is I had an opportunity to look at the layout, and here's the smallest die size. Here is the fastest one, and here's sort of one that's in the happy middle or so. And if you look carefully, what you can see is that part of the floor plan was kept the same, and part of the floor plan was changed. Maybe it was able to be changed, or maybe it was locked, I don't know. But I love to see this picture. Actually, my first reaction was, oh, we need to get a t-shirt with this first AI-driven chip. And they said, don't worry, we've already thought about that. I didn't know that, but it turns out that for hot chips, you can get your own t-shirt. Just click on that QR. Don't worry, it will come back a little bit later in the presentation. So bottom line of all of this, we've made enormous progress, but it begs the question where we're going to go next. And Walter Gropius, another well-known architect, says, architecture really begins where engineering ends. Well, we have no intent whatsoever to end engineering. As a matter of fact, our job, we feel, is to raise the level of optimality because it raises the entire picture. And of course, the way we've done that, you've seen in the previous example. So on top of Fusion, we put DSO, and initially it cut down on the design time. Pretty quickly, we're able to improve quality of results. And with the learning, there was another push forward of both quality results and time to results. Now the question we have is, do we think that we can start adding some microarchitectural optimizations on that and sort of illustrate this here as a way to raise the bar for all of us, especially for the architects that can then use this. And so the way to look at this is back to this graph, where the work that was mostly done so far is all in this vertical axis, cell optimization and many other things. But could we do something in the structural space? Clocks would be a good example. There are a number of other things we can do there. And then, of course, in the longer term, maybe at some point in time, it's even possible to revisit some aspects of functionality, maybe go as far as touch the software that's running on the chip and that one wants to optimize for. Now, here's the good news. We actually have made some progress in this, and I want to share that with you today. And so this brings us to very recently, July, last month. And in this case, it's an example of optimizing, again, for timing and power. And this was the best result that the designer had. So let's apply DSO in I don't want to call it traditional, it's a year old, but in what you've seen before. And very quickly, you can see that it improves on what's there, and actually about 5% power improvement, which is quite considerable. Now comes an interesting one. And that is the question of, what if we messed with the clocks? Well, notice the green points, and notice how they suddenly jumped. And my explanation for that is that some structure in the clock was changed that unlocked other opportunities or made them better. And you can see the progress is actually quite substantial, because another 13% of power improvement. Well, if that's possible, how ambitious do we want to be? Well, the ultimate ambition, of course, is to see if we can do something even in the functional space. And what that really means is a very big step into a different dimension, because that really means now going for total power. Power is an extremely difficult problem. Actually, it's sort of interesting to look at the architectural place, because Frank Gehry, great architect, said, you know, our constraint is really gravity. And then Renzo Piano, who must be a super yes-if person, is, well, you know, maybe crazy, but we keep fighting against it. Replace gravity with power. You got us. You got our field. Power is the limiter, is the physical limiter. That's the most difficult one. This is the ultimate yes-if boundary that we need to harshly push on. So let's try to do that. And in order to do that, I would like to briefly explain what's being done today and why it's so difficult. For starters, you know, power starts both at the bottom in manufacturing. What is the switching power of a transistor, the transmission power, and so on, all the way to the software. You run software, not too much power, and then suddenly there's a thing that just blows it out. So you have to really cover the whole spectrum to be at dynamic power. Well, in order to do that, there's a lot of steps you can take. You start from silicon to software, and bottom up you have estimation, top down you have essentially prototyping. And if we look at the levels of abstraction, it covers literally everything. Now, at Synopsys, we have a ton of tools. I won't describe all of them, but in different categories, it starts with exploration at the top, profiling, design intent, understanding it better, managing it, implementation, all the way now to 3D IC. Don't forget that thermal thing. And by the way, a ton of effort on low power design within the IP in a variety forms. Well, I'm going to use only two products in this explanation. One is actually ZeBu Empower, which we'll see in just a second, and the other is Prime Power. Now, what we do here is we try to explore first the activity loads from software. And here, the recent advance with ZeBu Empower is that we've found a way to massively improve the speed of that. So while in the past we literally could only do sort of kilocycles, now we can do megacycles. And that's important because you don't know when high intensity is going to occur. And in this case, we can quickly diagnose that the windows are pretty late, but we know at least where these moments occur. Now you take that data, and now you pass that through a capability to analyze what is the reason for this, what can we find out about this? And typically you get diagnosis that you then do something about. So here, for example, you may be able to improve it somewhat, but no matter what, you better look at the thermal impact of it. In this case, you may find, well, you know, some areas the voltage on and off didn't work as it should. And frankly, in some areas, maybe just a bug fix and there's some work ahead. So we use now this to see if we can use AI on this very complete deep flow. And starting with the same tools here, this time around, we look ZeBu in power to get the statistics of activity, prime power to diagnose the understanding how it impacts the circuit. And then the great hope, of course, is, well, so what are we going to get? We do have some results. And so remember, we were on this very same circuit a minute ago. And our objective was use the software workflows, go for total power, and let it run. And amazingly enough, immediately it starts to find some spots that are actually better. And yes, you can imagine this is a very complex set of computations, but the fact is, guided by learning and AI, we actually got another 10%. Another 10% here. And so it just shows to me that everything in the food chain matters. You change a transistor, it matters. You change the software, it matters, and everything in between. Actually, if you multiply these numbers out, what you get here is a 25.6% improvement in what we do for this chip. 25.6%, you know, that's in the league of a whole technology node or two. That's how big this is. And of course, we know what to do next, which is we are going to continue to push optimization into this picture, moving to more and more aspects, higher and higher levels of abstraction, knowing perfectly well that the difficulty level will increase because they all intersect. And of course, it begs the question, what are the roles that sit on top of that? Are we now talking about artificial architects? Or should we say, no, it is architects that use artificial intelligence to explore different options, to look at the pros and cons when addressing the opportunity space. Because after all, you're sitting in the middle of this picture. Great opportunity, a hunger for smarts in the world, and great optimality work being done by automation. Sometimes we can say aspiration, you are the inspiration, and we are the perspiration. Be it as it may, it is interesting that as architects, there's one thing that's important. Always understand what are the basics, what's the essence of the decision making on a direction that you take with your architecture. And this has been true since time immemorial because it's always built on the engineering underneath. Now, some of these buildings may have been less sophisticated than others. You know, by the time you have a pyramid decision, you know, most of the architectural decisions are sort of done. And you know, you may fiddle around with the burial chamber, but after that, it's mostly schlepping stones, right? You move 3,000 years forward, and when you find Hagia Sophia, an unbelievable building, where the whole question is, can you hold up that roof? And it's done mostly by being very heavy around it in the building. That changes in the next 1,000 years, as not only the roofs get higher, Taj Mahal, for example, or St. Paul's Basilica, and it gets more sophisticated, more aesthetics, more light questions, and so on. Be it as it may, the push up has never stopped, and engineering has always supported it. This is, in my opinion, sort of the fin-fed version of architectures. And granted, it's not about holding up the roof so much as using architecture to bring together state-of-the-art engineering and materials in every possible way. Well, what that leads us to is that you're sitting in the middle of a very interesting picture. And to get a little bit educated on this, I bought, 6, 7 weeks ago, a number of books on cathedral architecture, and very quickly learned that finding the essence is actually pretty straightforward. This is the essence. It's called gravity. Surprise, surprise. But what's interesting is the challenge with these roofs is that you have a round roof. It doesn't only push down, it pushes sideways. And so the whole trick is know the essence of how to dissipate this sideways push. And this is why they built these flying buttresses, to essentially compensate for the sideways push without just adding massive, massive weight. Now the amazing thing, the same weekend I got these books, I saw a presentation by Sam Nafziger. He did it at a conference, and I saw some of the slides, and for starters, this slide blew me away. Just the sheer beauty of this multi-tile device. But what was super cool was he had put the following arrows on it. And those are, of course, the data flows. And instantaneously, I saw the similarity between the data flows and the gravity flows being actually understanding the essence of what to do right to build something. And it was just so cool to see this because, of course, that puts us in the middle of this picture. The SysMore era has an opportunity that is huge because it brings together end markets and the best technology can do. Now, we often say success is the sum of our efforts. No, it's not. It's the product of our efforts. A single zero and everybody gets zero. That's just another way of saying, it's all about trust and teamwork. And what better way to represent it than with Escher's hands? And we know these hands well. For the last 50 years, we have used computers to develop EDA, that's used to develop chips that go into computers, to run EDA. We go around the loop. We fortify and strengthen each other. Now it's beyond that. You, the architects, have to guide the direction we take on the basis of the amount of automation that we can provide in extremely complex designs. And so by sitting here in the middle of this picture, you have truly an opportunity to impact the future, and the next 20 years will be of massive, massive impact to humanity. So with that, let me leave you with one of the greatest chips I've ever seen. I love these chips because beautiful chips are almost artworks, masterpieces. You can look at them, you can still see more into it. And I wonder if you know which chip this is. I'm cheating a little bit. Remember, builders of the imaginary. This is an artist, Gerhard Richter, who did this in 1992. So he actually looked forward where the chip world was going. We can learn a lot from that. Actually, I would argue that great engineers are often also great artists because we can imagine the impossible and we can deliver rubber meets the road. So on that note, I love this chip because it's my yes if. It's the yes of a commitment to you. Yes, we will deliver. We Synopsys will deliver 1,000x in productivity and capabilities to you in this decade. The if part is, if you and us can work together closely, we can not only be builders of the imaginary, we be catalysts of the impossible, the greatest job there is on earth. Such a privilege to talk to you. Thank you.
All right, well, thank you, Aart. That was a really exciting talk. During the talk, which was pre-recorded, Aart and I got a little chance to chat, and both agreed that the defining moment for us in realizing what ML was able to do was when we learned that how successful AlphaGo was, and in particular, in teaching itself to play, simply knowing the rules of the game, and then played against itself and became a world champion. And I think, you know, those of us who've been designing chips, if you apply those ideas and you understand what that means to what we do, which is very, very hard, but at the same time very regular, the possibilities here are incredible. So thank you for giving us a little insight into that. So we have about 10 minutes for questions, but then there's an hour break. So I'm going to go a little long. If you can tear yourself away and go to your own lunch, decide to do that whenever you're ready. Okay, so a first question. I have to get my computer here working. John Masters of Red Hat asks, do you believe machine learning can help with spec compliance on IP blocks?
Of course, you know, machine learning is like the snake oil that will be applied to everything. But on a more practical note, there are many things that can be checked automatically by essentially looking through rules. And that is probably not what you're thinking. You're thinking about, well, how can we actually apply stimuli to a model and at the same time figure out what is the coverage that you get on that model. And so all three of these elements are equally important, because if your model may be a great digital model but doesn't quite reflect the physical reality, you will miss certain things. And with many of the I/O interfaces, actually that's often the problem. Somebody just took a longer cable than USB spec said, and you cannot really detect that very easily on a digital model. But zeroing back on the digital model, assuming you have a very good model, now figuring out what the coverage is very much a function of how you can detect the errors and how can you stimulate the vectors coming in. And by the way, one of the mechanisms that sits in between there are the test structures. And so remember, testing is really accessibility and controllability. And and observability, sorry, is what I meant. And so when you combine all of these things, now you can absolutely start to learn from patterns how to stimulate your devices more effectively. And this is an area that we are going to see a lot of practical growth in. But to me, the most interesting really is if you make the intersection between verification and optimization and say, oh, and by the way, I will authorize you to add just a few control points. Could you dramatically change the picture? And the answer, of course, is yes, unless the control point screws up all your other optimizations. And that's why the space between verification and optimization is actually, in my mind, very much a continuum.
Great. Thank you. Ralph Wittig asks a question that we should all be wondering about, which is, how long does DSO take to converge typically? And I'll add to that, and what kind of machine resources are needed in some of these examples you're given?
Well, obviously, this is both a function of the size of the problem, its complexity, and the number of cores that you have. Most of these experiments were sort of in the 20-core type range and run from days to maybe a week or so to get through the whole experiment.
Great. And what sort of input does DSO need from the designer to explore these large spaces?
Well, the designer, of course, has a wealth of input, starting with the RTL that can be modified in different ways, starting with the areas of focus to focus the optimization on, but then every other variable, the timing constraints, any other area constraints that you may have, because very often you're sitting in the middle of a floor plan with large blocks that may or may not be movable. And so each one of those are subject to some play. And I want to point you back to the one example that I particularly loved, which was the one where we let the system change the floor plan. And you may have noticed certain things changed and other things just stayed the same. Well, right there, there's a high degree of human control in influencing those things. And in all situations, I look at the optimization system sort of not any different than what we've had for the last 35 years. It's your ultimate estimator. And so people that understand more of the big picture can ultimately drive it a bit more in a direction where certain change that the machine itself may not be able to find can just be experimented with, and that's how you can still benefit quite a bit on top of what we accomplish automatically.
So, thinking back to a bunch of my experiences, with synthesis, I think designers had to learn and accept that the tools were going to change their code more and more, and we found over time, we went from data path designs that were very rigid to realizing you might not even do well to seed what you thought was right, but let the place and route tools go. Do you think we're going to need to loosen a lot of the non-real constraints and turn them more into suggestions in order to really free this up? And will the tools need to help encourage that?
I love your question, because my immediate answer would be yes, it's going to go in that direction, because you will gradually know where to trust that loosening something up is likely to get better results than by having it too fixed. Now, the reason, of course, you want to fix things is because you actually do know stuff. You know a lot of stuff as a good architect. And so starting with that, that's why I call the architectural position one that determines the key options. But once you have options, you can do experiments in different directions and see where are the sensitivities to the architecture. Where you should not be looking, where are the sensitivities to moving wires a little bit and gates a little bit and so on. There are so many of those that a lot of the benefits are actually in corners that you would never have thought about loosening things, because it was already loose. So we may as well optimize it for yield, for timing, for power, etc. And so the more we can align the tools to support your understanding of options, that is, I think, how we get now a multiplicative impact between the architect making the decision and the machine doing the optimality.
Great, thank you. Let's see, Raj from Western Digital is asking, what machine learning tools did you use? Is it DNL or something else? Anything you can share about?
Let me not go into that, A, because I'm not insufficiently knowledgeable to see what is right now the combination of algorithms that we use. And B, well, that's a little bit part of the sauce that Synopsys is adding to the menu today.
Okay. Another question I'd like to ask. Do you think we need new description languages, a new language other than the structural RTL we have today? I point back to, when you move from single-threaded programming to multi-threaded programming, you really want to express the problem very differently, both to express the parallelism and to enable the parallelism. And there seems to me there's a lot of ways in which RTL is over-constraining the problem, not just in the hierarchy. That's an obvious one, easy to solve. But even more, relatively easy. But even more generally, you're way over-constraining the problem with RTL.
Well, the answer is an obvious yes, although, I should really ask you that question. You're the pro at this, I'm not. But what is clear is whenever you can optimize automatically the lower steps, it moves you up a step as an architect. And then you say, well, if it had just known that parallel is okay and not just serial, it could do so much better. Yeah, well, why did you not tell it? Well, I couldn't do anything with it at that point in time. And so the optimizations are both supporting you and also somewhat your limiter. But in that context, if we can enrich the language step by step by essentially focusing more on the very optionality that you have to decide upon, this is how you will never be happy with what we have, and yet we will make you happy that you can move up. Because every new insight that you have and the tool cannot immediately absorb, you're going to say, well, this is still primitive stuff. And it is still primitive stuff. Here we are, I think, at the beginning of a whole new era for chip design. And at the same time, I'm the first one to say it feels like, first year of synthesis. And I remember well, when we went to the designers with the first designs, and we took their design, and in a matter of hours, were able to make it much smaller and much faster. Initially, they didn't believe it. Then they looked at it, they checked it out, and suddenly they found out, well, it is correct. And then a problem happened, which is now they thought, well, this is magic, can do anything. No, 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 we had a lot of work for the last 30 years to make it a lot better. And I think the same is going to happen here, which is the minute you have something useful, you say, well, but it's dark slow, and how come it cannot do this and that? And this is the reason it's such a privilege talking to you, because you are the cast of characters that can be our motivator to move up. You know that if we just did this thing and that thing, suddenly the jumps forward are going to be big. And that's what I sort of try to express a little bit with this circle that gradually fills up with capabilities as we try to catch up with you.
Good. So we have reached the end of the time period, but I'm going to keep going as long as we've got some questions and Aart is willing to answer them. But if you're the sort of person who wants to leave class as soon as the bell rings, feel free to go now. I do want to remind people during the upcoming hour-long break, please go look at the posters. Please go look at the Slack channels for our sponsors. Many of them are there to interact with you, and that's traditionally a very powerful part of Hot Chips. Let's go back and see what else we can find. Amaya from NVIDIA asks, while exploring the different area timing clock points, did all points pass the basic timing tests?
They have to. Otherwise, the chip doesn't work. And so the optimization really has, first and foremost, one objective. It is always the speed of the chips. Therefore, timing is completely irrelevant. Secondly, power is the other dimension. And depending on what type of chip you do, power is more important or timing. And so most of the changes that you can make are then optimization changes of moving things around, of determining what margins to build into the layout, and thus to impact things like yield, and then to respect the structures that you can't really modify, such as testing structures and so on. And so in that optimization, timing has always been the singular most interconnected part of the feature to optimize. That goes back all the way to the early days of synthesis, because while Synopsys is known for synthesis, it was synthesis with built-in timing verification. And of course, timing verification has become dramatically more complex with time borrowing, with moving clocks around, and looking at the statistics of timing. And so there's a reason that most people, when they get chips back, they ultimately do binning, because there's a statistical distribution on your timing. And we optimize not just the timing, we optimize the statistical distribution of those timings as much as possible, because that has a huge impact on yield if you have only one window of acceptability. If you can do binning, that means, well, if some things do better than expected, you sell them for more, and others, they go into less performant applications. So timing is probably the single most interwoven aspect of the optimizations we do. And as you know, there are many changes you can change in a design to meet timing.
Great. By the way, I should tell you there's dozens of comments coming in saying what a great talk it is, how much people enjoyed the relationship to architecture and all the architects you referenced. So thank you for that.
Well, I must add one thing, which is while this was running, Fred and I were talking about architecture, and I discovered that there's nothing in the talk that Fred did not already know. And he, too, is a person who loves the individual brick all the way to the multi-tile system, understanding so well that every layer really is dependent on the layers below. And so, it's a privilege to talk to you, Fred. Thank you.
Thank you. But that's not going to stop me from asking you some of the hard questions.
The hard ones now.
Sean from Google, great talk. What changes in licensing models are underway so that customers can throw 100x more compute at problems? Of course, Google would ask that question. Many tools in the industry end up encouraging the users of the tools to use them as little as possible.
It's fun that question comes from you, because my answer, of course, is it's so great that Google is making the compute available for free, and that solves all of our problems. Now, No kidding. Obviously, the license models have to sustain an ongoing flow of development, and that is true for Google. It's true for us. And one can look at licensing model where one looks at making it somewhat relating directly to the amount of utilization, or one can go with the standard models that we've had in the past, which is, well, it's the customer's challenge to either find the compute themselves or have it on the net. And so the good news is what we've been able to do, I think, is not unbelievably going crazy in terms of the amount of compute. Some of the most difficult things are actually the things that are done in the tools underneath, which is to constantly be able to assess the goodness of the solution. Remember, in our case, we're not dealing with, oh, you're winning a game and is there a very clear black and white outcome for that. No, we're doing an optimization of billions of parts with statistics of behavior around that, and then statistics of manufacturing through yield and area underneath that. And so assessing the state of affairs, so to speak, as one does the optimization is a big part of the computation. And if a human does the design, they have to do that as well. Now, the fact that we can do this in a much shorter amount of time, I mean, literally, we're talking months to weeks, does open up the door to economic benefits for the people using it to go to market much faster. Or, and I would predict that that is going to happen, we're going to see many more dedicated chips to every vertical application you can think about, because nothing better than tuning an architecture for an application to really get some speed out. And every architect knows that. And what we do is just try to implement it as well as possible. So again, the architect decides on the options of the architecture. We try to implement the optimality of ultimately the physical design.
Very good. There was a...
while you think about the question,
yeah.
Let me add something for,
sure.
I forget the name of the person from Google. And that is actually a big thank you. You mentioned it coming in, the Go game was the moment. It was the moment, because suddenly it became clear what was understood but maybe not feasible before, that this combination of deductive reasoning and pattern matching reasoning combined with a learning ability would open so many doors. And we've seen this. Of course, every one of our tools has oodles of machine learning in it, mostly actually to optimize the internal heuristics that deductive programs use. But the ability to now recognize patterns and learn from that is just an amazing gift. And so the moment was a very pointed moment, and full credit to Google to have just executed on that in a fabulous way. So we stand on the shoulders of giants, and a lot of giants in our past.
I can't find the question anymore, but I do remember it, which is, have you done anything with the DSO looking down into the standard cell libraries and potentially treating them as changeable?
There's a great question, because there's independent of that question, let me give you the grounding first, which is there's a major push for DTCO, Design Technology Co-Optimization. And that is essentially trying to link directly, literally, the materials, the structure of the individual switching transistor devices, and of course interconnect and layering, and then go to the basic foundational libraries, and then go from that all the way into, let's say, processor core. And then ask the question, if I tweak something at the very bottom, what happens to that core? And so we have been able to establish this loop on the computer today. And by the way, the alternative is to do exactly the same, except you have to send it through a fab. I don't have to tell you that takes a long time before you get results. And that's a very big if the modeling is good enough, then you can do a zillion experiments before you actually send things through the fab. And so if we can close that loop, of course, machine learning, if the loop is fast enough, can be applied to say, well, what are the variables that through this entire stack have the biggest impact? And maybe that is actually the essence, thanks for the question of the presentation today, is that we're no longer talking about individual steps. We're talking really of a whole process of creating something. And, this is why I think we have moved from scale complexity, which is sort of the traditional Moore's law, fantastic exponential, to systemic complexity, because it's the intersection of many different problems at many different layers of abstraction. And remember, if there's one thing to take away from the presentation is additions are dead. It's all about multiplication. A single zero, and everybody gets zero. And so that applies to very different types of problems all intersecting.
Great. I think I'm just going to do one more question because we are getting pretty long here. Gopa Bandhu from UC San Diego asks, beyond EDA and digital, can AI tools explore custom analog designs and optimizations in that space?
I think the answer will be yes, and partially it will be yes because that is not that far away from what I just described as DTCO, which is the understanding where the component of the physics is much more open in any form of custom design, because we fundamentally dealing with electrical waves instead of digital signals, and so there's no reason whatsoever to not assume that here too, replacing for starters manufacturing as the experimental base with a computer model, that once you have that, you're home free to try all kinds of stuff. And so if you now added to that, for example, notions of yield, notions of what happens if you have slight shifts in the manufacturing, what does that do to these circuits? You certainly have a lot of variables, and great custom designers actually know what to do with those, but for a lot of situations, that's actually quite complex.
All right. Thank you very much, Aart, for the questions answering and for a really intriguing and fun speech.
Thank you, Fred.
All right.
A pleasure.